Good day, everyone. Thank you for opening this video. My name is Chen Chen, and I am a Senior Research Fellow at the School of Civil and Environmental Engineering at Nanyang Technological University, situated in Singapore. My research interests lie in smart construction, smart manufacturing, and sustainability. The topic of today's presentation is about Singapore's digital construction. For today's presentation, I have planned the following content arrangement. Firstly, I will discuss digital transformation. Next, I will describe the trend of offsite construction. Thirdly, I will be talking about digital twins, followed by the future of the factory. Then, I will explain IDD and DfMA. Finally, I will address the concept of a leagile supply chain. We will begin with the first section, which is focused on digital transformation. The words digitization, digitalization, and digital transformation are used interchangeably, but their meanings are different. Digitization means to make something digital. For example, scanning a paper document and save it as a PDF file is digitization. Digitalization, on the other hand, involves the use of digital technologies and digitized data to enhance or streamline processes. Moreover, digital transformation is about using technology to enable new ways of working and driving innovation. Embracing digital transformation is no longer a choice, it's a critical necessity. When businesses embark on the journey of digital optimization, they take the first step towards transformation. This endless journey begins with a fragmented state and progresses towards a compliant, secure, and digitally enabled operating model that revolutionized the way customers, employees, partners, and stakeholders perceive the business. What's the relationship between Industry 4.0 and digital transformation? Well, Industry 4.0 refers explicitly to changes in manufacturing, while digital transformation can be applied to any business in any industry. Throughout history, the industry has undergone four significant revolutions. The first industrial revolution, which began in the 18th century, brought about steam power and machines into production. The second industrial revolution began in the 19th century and was characterized by the discovery of electricity and the introduction of assembly line production. The third industrial revolution, which started in the 1970s, replaced human workers with intelligent machines, programs, and algorithms that partially performed the work, making it faster and more efficient. Currently, we are experiencing the fourth industrial revolution, also known as Industry 4.0, which can be defined as the integration of intelligent digital technologies into manufacturing and industrial processes. Germany is widely recognized as a leader in the implementation of Industry 4.0, which was first coined at the Hanover Fair in 2011. The term Industry 4.0 refers to a new era of technology that encompasses a wide range of technologies and paradigms such as AI, machine learning, and big data. The objective of Industry 4.0 is to make factories more autonomous, real-time, and decentralized. Both horizontal and vertical integration are crucial components of Industry 4.0. Horizontal integration involves connecting the factory to the entire external value chain through a well-designed and integrated workflow. Vertical integration, on the other hand, allows for all levels of the factory to be connected from a hierarchy. This results in the creation of smart manufacturing and intelligent factories which are capable of making data-driven decisions and optimizing production processes. It seems that there's still some debate about what exactly Construction 4.0 means on a global scale. Some folks think it's just a straightforward extension of Industry 4.0 in the construction sector, while others see it as a way to bring together all the exciting new technology trends happening in the industry. Either way, what's really exciting about Construction 4.0 is that it's connecting physical and digital spaces like never before, thanks to the cutting-edge technology. The Industry Transformation Program, worth 4.5 billion Singapore dollars, was launched in 2016 by the Future Economic Council to drive the transformation of 23 industries, including manufacturing and the built environment. The Construction Industry Transformation Map, which is a part of the Industry Transformation Program, has set a goal to train 80,000 professionals. 3 key areas have been identified as crucial for the industry's transformation. These areas are design for manufacturing and assembly, green buildings, and integrated digital delivery. We will now proceed to Section 2, which focuses on offsite construction. The construction sector is currently experiencing a significant transformation, thanks to several benefits such as better on-site health and safety, improved quality, reduced labor and cost, shorter project time, and eco-friendliness. The industry is moving towards manufacturing and mass production. As a result, general contractors are turning into manufacturers. The concept of supply chain management was initially developed for the manufacturing industry, but in recent years, the construction sector has also started adopting its principles. Unlike in manufacturing, in construction, the client is the one who starts a project, which means that the construction supply chain is often seen as a process that begins and ends with the end user. A major characteristic of the construction supply chain is that each client has unique requirements, which means that the construction supply chain must be adaptable to ensure efficiency and effectiveness. Construction projects pass through 3 major life cycle phases: design, construction, and operations. Building Information Modeling, or BIM, stands for a collaborative approach that uses digital models to consistently record, manage, exchange, and coordinate all data and information related to a building throughout its life cycle among the parties involved. By doing so, BIM ensures that all stakeholders have access to accurate and up-to-date information, improving the efficiency and effectiveness of the project. Over the years, contractors and subcontractors often face challenges caused by poor communication between them. One of the biggest problems is delays in getting equipment and materials to the job site. But now, with Industry 4.0, we can connect these one separate supply chains and create a system that everyone can see and work with. This will make things smoother for everyone involved in the process. The construction industry is one of the biggest energy and resource guzzlers across the globe. With the growing need to reduce carbon emissions, it's about time that the construction industry hops on board with the circular economy. The circular economy is all about preserving materials and restoring nature. Basically, it's a system where products and materials are kept in use through processes like maintenance, reuse, refurbishment, manufacture, recycling, and composting instead of being thrown away as waste. There are 5 levels of prefabrication that we can use to classify modular construction methods, ranging from materials to complete units. Level 5 is very similar to Level 4, where the majority of the construction occurs off-site, including interior finishes and final furniture in a volumetric module. The key difference between Level 4 and 5 is that Level 5 modules are full living units. Housing development board flats are the majority of Singapore's housing stock. HDB was one of the first to adopt prefabrication technology, using precast components in the construction of flats since the 1980s. For every HDB residential project, precast components make up about 70% of the entire structural concrete used. The use of prefabricated bathroom units is mandated for HDB projects. The use of prefabricated, pre-finished volumetric construction is required for some selected HDB projects. With the technical experience gained over the years, HDB has been able to develop its own brand of precast technology, known as the HDB Precast Building System. It is an array of 2D precast components combined to form the entire building system. Offsite construction has become increasingly popular due to its numerous advantages. One of the latest technologies that support this approach is PPVC, which supports the DfMA concept. In Singapore, the majority of built-to-order flats launched nowadays are constructed using the PPVC method, indicating its growing acceptance and success. The precast industry is set to play a crucial role in driving the transformation of the entire built environment sector. To boost the local supply of precast components, Singapore has established integrated construction and prefabrication hubs. These are multi-level advanced manufacturing facilities that feature a high level of mechanization and automation. To cluster construction facilities such as aggregate storage yards and ICPHs, Singapore has also developed integrated construction parks. We will now proceed to Section 3, which is dedicated to discussing digital twin technology. The concept of digital twins isn't exactly new. For over 30 years, we've been using digital modeling in CAD software to create new products and digital maps in GIS systems to manage utility networks. However, what's really exciting is that we now can add live data to these models through sensors and IoT networks. A digital twin isn't just some ready-made software package you can just buy off the shelf. It's actually a continuous process of development where you keep adding systems, sensors, and data to the twin. As devices become more interconnected, analytical systems improve, and we discover new ways of integrating digital services, buildings and cities can gradually become smarter. By analogy, The evolutive twin starts blind, deaf, and mute. It is a static twin in its first life stage. As more and more data are added to it, it starts to open its eyes and gains more awareness of its surroundings. Eventually, with the help of sensors, it can see, hear, and even talk. However, the digital twin still needs humans to control it. If we want it to be truly independent, we need to make it artificially intelligent. Over time, as the digital twin learns and adapts to different situations, it becomes more and more intelligent. Eventually, it becomes fully autonomous, able to make its own decisions and run its environment without human help. Digital twins are created by combining many different applications and data sets. Sensors are gathering data at an enormous rate, and this is ensuring that what used to be static, disconnected assets are becoming part of a lived digital ecosystem. The data streams will assist the building owners to leverage such data in AI and machine learning applications. The adoption of property technologies in buildings will enhance the asset and continue to maximize efficiencies while improving worker productivity and enhancing occupant comfort. A digital twin is like the tech version of a project or asset. It comes from the BIM process and keeps changing based on real-time data once the asset is in use, which makes it pretty cool. Digital twins, according to their purposes, can be described in 5 different ways: descriptive, informative, predictive, prescriptive, and transformative. Digital twins are complex systems that cannot be purchased off the shelf. They are the outcome of significant effort in systems integration, and it is unlikely that this will change anytime soon. On this slide, you can see a summary of the interaction between value generation, common challenges, and enabling technologies. From a technical point of view, the main challenges in developing digital twin technologies including ensuring data security and management, improving data quality, reducing latency, performing real-time simulations, fusing and assimilating large-scale data, utilizing intelligent data analytics, enhancing predictive capacity, promoting transparency, and generalizing technologies across a wide range of application areas. Now, let's move on to section 4, the smart factory. The terms smart manufacturing, smart factory, and smart industry all pertain to the integration of cutting-edge technologies and data analysis in order to enhance manufacturing processes and boost productivity. These innovative technologies include the IoT, AI, robotics, and automation. In 2022, the semiconductor community proposed the Industry 4.0 Readiness Assessment Model, as this slide shows, as a tool to help organizations assess their progress in deploying Industry 4.0 technology. Smart factories rely heavily on cloud-based ERPs to achieve success. This ERP serves as a central hub for collecting, maintaining, and sharing both operational and financial data. By modernizing and migrating ERPs to the cloud, organizations can fully unlock the potential of smart factories. An ERP system is responsible for managing all business processes. However, While some ERP software solutions offer Gantt charts for planning and scheduling, configuring them can be challenging as they are not specially designed for this purpose. Additionally, ERP systems often struggle to facilitate scenario analysis, since creating hypothetical resources within a lived system can be complex. On the other hand, an APS application provides more advanced tools and algorithms for what-if scenarios compared to ERP software. Although ERP and APS systems can be used independently, they work best when used in combination. Let's take our next step forward to Section 5. Since 2015, buildings in Singapore with a floor area of over 5,000 square meters are required to submit BIM model data for design, structure, and equipment when applying for building permits. In 2017, the Singapore Building and Construction Authority launched an implementation plan for integrated digital delivery, which aims to encourage more built environment sector firms to go digital. IDD uses cloud and digital technology to integrate stakeholders in the building lifecycle management. DfMA is short for Design for Manufacture and Assembly. It's a combination of DfA and DfM principles. The idea behind the DfMA is to make it easier to assemble products and improve the efficiency of component manufacturing. It takes an overall view of the manufacturing and assembly designs to identify any unnecessary functions, parts, or processes that could be streamlined to make the product development process more efficient. Based on focus group discussions with leading DfMA firms, the key IDD use cases have been identified along the DfMA value chain. These use cases include the DfMA configurator tool, collaborative production planning tool, digital submission and approval, and digital inspection. Additionally, it is crucial for the IDD for DfMA framework to meet the client's needs by enabling them to monitor the overall health of the project. Now we have reached the final section of our discussion, which focuses on the concept of a leagile supply chain. Precast products have large volumes as well as a wide variety, so they lie in the fourth quadrant, where the leagile approach can be applied effectively. Leveraging Industry 4.0 technologies, achieving a leagile supply chain becomes possible. Leagile is a term that combines the characteristics of two approaches, namely lean and agile. The lean approach, which prioritizes efficiency, is more appropriate for relatively stable markets where the cost is a significant concern. On the other hand, the agile approach, which emphasizes the quick response to market needs, is more suitable for rapidly changing markets, such as the fashion industry. The application of leagile requires the identification of a material flow decoupling point. The position of this point depends on the maximum lead time that a customer is willing to accept, and the point where product demand variability becomes dominant. A leagile supply chain uses a postponement strategy. The goal of the postponement is to delay the customization as late as possible in the supply chain. A pull system is a lean manufacturing strategy. There are different types of production planning and control systems in the pull systems. One of them is the Kanban system. When the inventory levels drop to a predetermined minimum threshold, a Kanban signal is triggered, indicating that more inventory needs to be produced or ordered. On the other hand, the MRP is a tool used for calculating the raw materials, subassemblies, and components required by a manufacturer to produce a product. OPT and DDMRP are hybrids of Kanban and MRP. OPT concentrates on constrained resources, while DDMRP focuses on critical resources. The aim of the solution is to protect the weakest link in the system. In order to achieve optimization, it is essential to have a clear goal. However, these goals may vary among different departments in manufacturing organization. Even though these goals converge to the same optimal solution, they generate different near-optimal solutions with an early truncation in the optimization search. In manufacturing environments, there are hierarchical levels of planning and analysis. The construction supply chain has a lot of uncertainties to deal with, like getting the right raw materials, meeting deadlines, and getting things delivered on time. This slide displays the issues faced by precast factory insiders. This slide displays the obstacles that lie ahead. This is the end of my presentation today. Thank you for your time and attention.